Hello MCT4C, we're on polynomial functions day 6 and we continue with comparing polynomials. Remember that we are restricting ourselves to linear, quadratic, cubic, and quartic. So if we are given the table, we can do two different things. We can draw the graph, at least in a limited way, and we can find the equation. So I've got two examples below. On the first one, we have a table of values, x, y, minus 2, 7, and so on. The first thing we should do is to calculate the first and second differences and so on and determine what type of an equation it is. So for our first differences, 5 take away 7 is negative 2, 3 take away 5 is negative 2, and so on. Our first differences are all the same, therefore it is linear. And we know that this function is decreasing, so we have a linear equation with a negative slope, and those first differences are 2. So we know that our equation will be y equals negative 2x plus b, where your negative 2 is your slope, but also comes from the first differences. Our b is our y-intercept, and we have been given the y-intercept as 0, 3. So it's really sweet when we have a line. It takes a lot less work. So minus 2x plus 3 is our equation. We can draw that by plotting the points, or assuming that that is an equation that goes for infinity. So we're going to do both. One point is minus 2, 7. 5, 6, 7, there. Minus 1, 5. Oops. 0, 3, 1, 1, and 2, minus 1. We have a line that has a y-intercept of 3 and a slope of down 2 over 1 from grade 9. We should have a nice sweet line through. It's not liking me. And I'm going to label that y equals minus 2x plus 3. Second polynomial function that we have has the table of values, minus 3, 16, and so on. I would look first at my first differences and see if they are the same. So 13 minus 16, minus 3. 6 minus 13, minus 7. Minus 5, 3. 17, make sure I've got my signs correctly, 37. Let's have a look at our second differences. Minus 7 take away minus 3 is minus 4. Negative 5 take away negative 7 is 2. Make sure you do lower one, subtract higher one. 8, 14, and 20. And second differences are not the same either. It is not a quadratic. Let's look at the third differences. 2 take away negative 4 is 6. 8 take away 2 is 6. 14 take away 8 is 6. And 20 take away 14 is 6. So I'm glad that my arithmetic is correct. Secondly, we know that this is a cubic because our third differences are the same. And we expect with a cubic that our third differences would be 6. So that tells us that our a value, or our leading coefficient, is 1, because that is the third differences are 6, as one would expect. So we know that our equation is going to start with y equals 1x cubed plus bx squared plus cx plus d. So this can help us find our equation. We can plot the points as well in order to graph this, but I would like to continue just for the moment finding the equation. This can get a little ugly, but we do know the y-intercept is our d value, and we have been given that the y-intercept is 1. So far we have that y equals x cubed plus bx squared plus cx plus 1. What we don't know is the b and the c, and that we would like to find. So since we have a table of values, we have a number of points. If I choose 2 nice points, I can solve for B and C using a system of equations. I'm going to choose the nicest ones, which are the points 1, 4, and the points 2, 21. I'm avoiding negative numbers. So first step is I'm going to substitute the point 1, 4 into that equation. So I have 4 instead of y equals, I put a 1 wherever I see an x. 1 cubed plus b times 1 squared plus c times 1 plus 1. Going to tidy that up a little bit. I have 4 equals 1 plus b plus c plus 1. Just one more tidy up. On the right side, I have 1 plus 1, and I have b and c. So if I now subtract 2 from both sides, I have a simple equation. 2 equals b plus c. Secondly, I'm going to use my other point. Substitute the point 221 into the equation. 21 is for the y, and wherever I see an x, I will put a 2. 2 cubed plus b times 2 squared plus c times 2 plus the number 1. Now I have some tidy up to do. I have 21 equals 8 plus 4b plus 2c plus 1. Collecting my like terms, I have 21 equals 9 plus 4b plus 2c. And I'm going to subtract 9 from both sides. This leaves me with 12 equals 4b plus 2c. And just to use up paper, I'm going to do one more step of dividing both sides by 2. 6 equals 2b plus c. That is as simple as I can get an equation coming from substituting the point that I know and another point that I know, and I have 2 equations and 2 unknowns. So from grade 10, we know how to solve those. I keep making this page smaller. But if I have the equation 2 equals b plus c and 6 equals 2b plus c, then I can either use substitution or elimination to get rid of, so call that equation 1 and that equation 2, to get rid of one of the variables. I have decided that I am going to use elimination. Equation 1 subtract equation 2 will get rid of my c's, and then I can solve for b. 2 take away 6 is negative 4. b take away 2b is negative 1b, and my c's have disappeared. I am left with b, if I divide both sides by negative 1, equals 4. If I know that b equals 4, I'm going to go back to equation 1 because it's the nicest. And 2 equals, well, if I know that b is 4, I'll put a 4 into that equation, and I can solve for c. Subtracting 4 from both sides, I have negative 2 equals c. Quick mental check. Do those two values of b and c work in both my first equation and my second equation? I'm going back up to the first equation to check. Does 2 equal 4 plus negative 2? Yes, it does. Going to the second equation. Does 6 equal 2 times, my b value is 4, plus a negative 2, which was my c value? 6 equals 8 plus negative 2. Yes, it does. It works for both of those equations. I have found b and c. Scrolling back up, my equation is y equals, putting it all together, y equals x cubed plus my b value is 4. Sorry, that's a cube. X squared plus my c value was negative 2. X plus 1. You can put that plus sign there or not, it doesn't matter. We have come up with our equation for that table of values, and it took a great deal of work. We can draw that function, or we can plot the points from example 2. I'm going to do it in red. I'm going to plot the points, and we're going to verify that that's what we should observe from what we know about polynomial functions. So my points are, I'm doing the pretty ones first. 0, 1, 1, 4, 221, and I'm already off the page. Yep, way up there. Minus 1 is 6. Minus 2 is 13. And again, I'm off the page. So in a very limited way, I have some places where that graph hits. But since I know my equation, y equals x cubed plus 4x squared minus 2x plus 1, I know about the end behavior. I know for a cubic that as x with a equals 1, I know that as x approaches infinity to the right, my function itself will approach infinity. But as x approaches infinity going to the left, negative infinity, my function likewise should be going downwards. So I don't have the whole story with my points. I know that it is going upwards, but I don't know how it behaves exactly. I just know it approaches that direction. I know on the left side, it looks like it is reaching upwards, but at some point it must come down, because as we go to the left, that function approaches negative infinity. So it is better to have an equation in order to graph most accurately. If we are given a graph of a function, we can determine end behaviors, possible degree, the domain and range, and intercepts. So for the first one, let's start with the end behaviors. As x approaches infinity going to the right, our function is approaching infinity. As x is going to the left, our function is going downwards. Possible degree. Following our chart that we filled out from page 85 in your textbook, this is certainly an odd degree polynomial with that end behavior. Following with the number of intercepts, so I'm skipping a little bit here, number of x-intercepts. We definitely have an x-intercept right here. And it appears that we have one here that looks like it changes direction at that point. So it looks like it could be a cubic. We have two x-intercepts, and it's an odd degree polynomial, so it appears to be a cubic. The domain and range also follow a cubic. The domain is anything goes. It's an element of the real numbers, and the range as well will go upwards and downwards forever. Also can be any real number. The second one, let's look at the same things. Looking at the end behavior, as x goes to the right, the function goes upwards. And as x goes further to the left, the function goes upwards. We find that type of end behavior in an even degree polynomial. There are two x-intercepts. at 3 and at 4. But it does not appear to be a quadratic because it has more turning points. It turns around here, and around here. It looks much more possible that it would be a quartic. The domain and the range. The domain is x can be any real number. It goes to the left and the right forever. The range, however, has restrictions. Y is greater than or equal to that minimum value, which we see here between 3 and 4, and it is a real number. When given the equation of a polynomial function, we can state the possible number of x-intercepts, the possible number of turning points, maximum, minimum, end behavior, and y-intercept. We can get a lot from an equation. First example, y equals x cubed plus 6x squared minus 2x minus 1. So this is a cubic, or an odd degree, with a equals 1. That tells us a number of things. End behavior. As x approaches infinity, y approaches infinity. It goes upwards to the right as x goes to the left. The function itself goes downward. Because it is a cubic, there are up to 3 x-intercepts. Possible numbers of turning points. Can't spell. Sorry. Possible number of turning points. We can have up to 1 less than the degree, so up to 2 turning points. And the y-intercept is -1. If we were able to factor this, we would have better luck at finding maximums and minimums. But the equation can give that to us if we are able to manipulate it. Let's look at the next example. Sorry, I just went back for a second. We can add to that. We can often give the domain and range if we have the equation, just from our knowledge of those particular functions. If we have a cubic, our domain is the real numbers, and the range is also the real numbers. That can help us in our graphing as well. Okay, on to the next. I breezed over something that we can look for when we have a table of values. So if we are looking at a table of values, I did an example for you at the beginning that looked at first and second and third differences very quickly. And I made some statements about those differences I just thought we should write down. So for a linear function, you know that the first differences are equal. And the first differences are m, the slope. We got that in grade 9 when we looked at just 2 points, which are really finding the first differences. But we said your slope comes from finding your first differences. If they are consistent throughout the table, all your first differences are equal, you have found the slope. With a quadratic, we know that the second differences are the same. For y equals x squared itself, which was our parent function in grade 11, we noticed that the second differences were 2. So that if I'm looking at a slightly altered equation, say y equals 3x squared, then I would expect that my second differences would be 3 times 2, or 6. So the one that we want to remember is that for the basic y equals x squared, your second differences are 2. That can help us determine what the leading coefficient is. So if we find that our second differences are all 6, then we know that our leading coefficient is 3. For the cubic, we would expect that our third differences are the same. And for our basic cubic, y equals x cubed, our third differences are 6. So that if we alter and have a leading coefficient something other than 1, let's go with 4x cubed, then our third differences will be 4 times 6, or 24. So working backwards, if we find that our third differences are equal, and they're equal to 24, then we could tell that our leading coefficient is 4 for a quartic. Our fourth differences are equal, for a basic quartic. Our fourth differences are equal to 24. So let's do one. If I have negative 2x to the fourth, then I should observe that my fourth differences are equal and equal to minus 48. So that I can work backwards from my understanding of the differences to find my leading coefficient. So those would be interesting little facts to put down on your cheat sheet. It's something that could help you. Let's look at a few examples. The first one has degree 2. If I were to do the FOIL on that, multiplying out and expanding, I would have an x squared term. So I have a quadratic. I know quite a bit about quadratics. This one has a leading coefficient that is positive. So I have an even positive, even degree, positive. So I know the end behavior. As x approaches infinity, the function itself increases. As x goes to the left, the function itself also increases. I know my x-intercepts because it's in factored form. There are 2 of them. The first one is 1, and the second one is 2. My leading coefficient is 2. I've said that already. Let's go to the next one. Y equals negative 3, x minus 1, x plus 2, x minus 3, again in factored form. I know that my leading coefficient is negative 3, and I have a cubic. So this is an odd degree. An odd degree polynomial that's negative. So from my chart that I keep at my fingertips night and day, then I know my end behavior. As x goes to the right, then the function itself goes downward because of the negative leading coefficient. As x goes to the left, then the function gets larger. I know that I have 3 x-intercepts because it's in factored form. I'm trying to convince you. 1, -2, and +3. The next one, y equals x minus 3 squared. It is a quadratic. There is an invisible leading coefficient of 1, positive. So it is a positive even degree polynomial. So we know the end behavior. As x approaches infinity, this function increases. As it goes to the left, the function also increases. This one has one x-intercept of 3. Just checking that I've got everything that I did in the last one. Yep. Okay. Third one, y equals x minus 3 squared times x plus 1. This one is a cubic, has degree 3. Its leading coefficient, again, is invisible 1. So I have an odd, so that tells me odd. Positive, that tells me what to look for in my chart. So an odd degree polynomial that's positive. So my end behavior, as x approaches to the right, the function itself increases. As you go further to the left, the function will decrease. I have 2 x-intercepts. I have an x-intercept of -1, and I have an x-intercept of 3. It has a square sign. That's going to tell us something special as we look ahead. The next one. If I were to expand y equals x plus 2 squared, x minus 4 squared, I would end up with a quartic. Quartic. I have an invisible a equals 1, so I have an even positive function. So on my chart, that will tell me my end behavior. As x approaches the right, it will also increase. I just don't want to lie to you, so I keep checking here. As we go further and further to the left, the function will again increase upwards. X-intercept, again, both of these have a double, but we have 2 x-intercepts. One is -2, and one is +4 from last year. The next one is a cubic with an invisible leading coefficient of 1. So we have a positive odd degree polynomial. So that will tell us our end behavior. End behavior, as we go to the right, the function itself will increase upwards. As we go to the left, it will decrease downwards. X-intercept. We have an x-intercept at 2. Let's fill in the info for the last one, and we'll just quick sketch a couple of these. X plus 3 cubed, x minus 4. We are going to have a quartic. We have an even, because it's a quartic. Positive, even degree. Positive, because there's an invisible a equals 1. So we know our end behavior. As we go further to the right, the function increases upwards. As we go to the left, the function increases upwards. We have x-intercepts of 4 and -3. This x-intercept is of order 3. Right here, order 3. This x-intercept is of order 1. If we go to this function that we looked at briefly already, we have two x-intercepts, one at -2 and one at 4. This one is of order 2, and so is this one, order 2. That tells us that there is a turning point on the x-axis at both of those places. Not just a place where the function will pass through the x-axis, there is a turning point. So, we know our end behavior. As I go further to the right, it's going to increase, and as I go further to the left, it's going to increase. My x-intercepts are at -2 and at 4. And because they are of order 2, there will be a turning point there. So my function will increase to the right and increase to the left. And we have a turning point. Instead of passing through the x-axis there. This is order 2 as well. So we will have an x-intercept. Let me just clean some of this out for a second. Okay. X minus 3 squared has order 2. That means we have an x-intercept at 3, order 2. Means that there is a turning point there. It doesn't just pass through the x-axis, whereas the x-intercept of -1 is not a turning point. It's an x-intercept, so we had our end behavior written down as well. It's an odd cubic, a positive cubic. So as we go further to the right, we're going to increase upwards. As we go to the left, we're going to decrease. So we've got this that we know. We know that we have an x-intercept at -1, and we have an x-intercept at 3 that is a turning point. So we're going to have a function that passes through, but does a turn. So we knew a lot more about that than we thought we did, going from the equation when it is in factored form. The following three functions can give us some interesting observations that we would like to conclude this lesson with. If y equals x to the 4th plus x squared, I can factor that as x squared times x squared plus 1. Factored form can tell us a lot of things. So this is an even degree function that's positive. So we know what happens as we go to the right, it goes upwards, and as we go to the left, it goes upwards. And I know that I have an x-intercept at 0. Because this bracket can never be equal to 0. X squared can never be -1. So I have a function that has an x-intercept of 0, increases to the right and to the left. It looks like a quadratic, but it is a nice balanced looking graph. The next one, y equals x to the 4th minus 3x squared plus 6, also has a nice even look to it. It will increase upwards as we go to the right and to the left. It has a y-intercept of 6, and that is what it looks like. Oops, should be even on the left and the right. Let's try that again. There. Should be a nice balanced looking graph from looking on my graphing calculator. For the next one, we have a quadratic that is up 8 with a negative leading coefficient. That means as we go to the right and we go to the left, it's going to go downwards. We knew that from grade 10 and from the polynomial discussions that we've had. Notice that all three of these functions are perfectly balanced, if I could draw a little better, about the y-axis. These are called even functions, not even degree. That's different. These are even functions. And that is when it is symmetric with respect to the y-axis. Even functions. A function is even if it is symmetric with respect to the y-axis. We can do a quick check to determine whether a function is an even function by the following. If f at x equals f at negative x, it is even. So if I were to replace x in my function with negative x and still get the same function, the same graph, it is even. So for the first one, if I were to replace x with negative x and I tidy it up, negative x to the power of 4 becomes positive x to the fourth. Negative x squared, if I were to square it, becomes positive x squared. It hasn't changed my function at all. So f at minus x is the same thing as my original function. It is an even function. And what it looks like is perfectly balanced around the y-axis. Same with the second one. If I were to put a negative x there and there, put them to the power of 4 and to the power of 2, I would end up with what I started. It won't change the function. It is an even function. For this one, if I replace my x with negative x and tidy it up, I will get positive x squared plus 8. I get my original function. It is an even function. And what it would look like is balanced around the y line. For the second set, if I were to graph y equals x cubed plus x, I happen to know that I can factor that. So I have an x-intercept at 0, like the one before. This will never give me a 0, so I've only got one x-intercept. I know that I have an odd degree because it's a cubic, positive, so that I know that its graph, as we go to the right, will increase, and as I go to the left, it will decrease. I am going to have a function that looks like that. That is not an even function. It's not balanced around the y-line, but it is something special in its own way. The second one, just quickly, if I were to just factor that out, I have x squared minus 5. I have two x-intercepts. 3 x-intercepts, I'm sorry. My x-intercepts are 0 from that. And if x squared were to equal 5, I would have another x-intercept. I would have one at root 5. And I would have another x-intercept at negative root 5. That's not the big idea right now. I just want to get you a drawing. I know because it is an odd positive that it is going to go upwards as we go to the right. down as we move to the left, and I have these three x-intercepts. So I have a function that looks like that. Those two functions are called odd functions. They are odd degree as well, but that's different. Odd degree just is because it's a cubic. An odd function, not just weird, it has symmetry in the origin. So if we could flip this part about the origin, we have a symmetric graph over here. We call that an odd function. And we can determine whether something is an odd function and then get a sense of what it looks like by this rule. If you throw a negative sign in front of your function, you will get the same thing if you replace x with negative x. So for example, this one. If I throw a negative in front of the entire function, I should get the same thing as replacing the x's with negative x. So let's see what we get when we do that. Negative x cubed plus 5x. Is that the same thing as replacing f at minus x? Is when I replace each x with negative x. Cubed minus 5 times minus x. If I tidy that up, I will get negative x cubed, because I've got 3 negative times negative is negative. And for the second term, a negative times a negative is a positive 5x. So this is negative f at x, and it is identical to f at negative x. So putting a negative in front of the function is equal to a negative inside the function. You have an odd function, and it is symmetric in the origin. For a check of the following three functions, we're going to determine if it has line symmetry about the y-axis. In other words, is an even function. Has symmetry in the origin, is an odd function, or neither. So for f at x, each term in this function is even, and we assume that it is an even function. That's what it looked like in the examples I gave you before. But let's check. If it is true that it is an even function, then f at minus x would also be the same as the original function. So I am going to replace my f at minus x is minus x to the power of 4, take away negative x squared plus 2. That is my f at minus x. Let's tidy that up. If I do negative x to the power of 4, I have negative x times negative x times negative x times negative x. I have positive x to the 4th. Take away. Negative x squared is 2 of them, so it's negative times negative is x squared plus 2. That is identical to the function that I started with, so f at minus x is equal to f at x. This is an even function. It will have line symmetry, just like we put a mirror about the y-axis. G of x. Each term is odd. We would assume it would be an odd function. Because my example showed ones just like that. But to be sure, we want to prove that it is an odd function, we should show that f at minus x, replacing the x with negative x, is the same as throwing a negative in front of the entire function. Let's look at f at minus x, and over here I'm going to look at negative f at x. F at minus x is where I replace each x with a negative. So negative x cubed plus 3 times negative x is f at minus x. Going to tidy that. A negative x cubed will be negative x cubed because I've got 3 of them. Positive times a negative is a negative 3x. Negative f at x is when I put a negative sign in front of the entire function, which was x cubed, that's 3x. And if I do distributive law on that, I will get negative x cubed, negative 3x. Those two are the same. Since f at minus x equals negative f at x, this is an odd, sorry, not an odd degree, an odd function, and it has symmetry in the origin. Last, h of x. H of x is a cubic it could be odd, and have symmetry in the origin. But we need to prove it. If it is odd, f at minus x is equal to negative f at x. F at minus x, I'm going to replace each x in our original h at x with a negative x. So I have negative x cubed plus 2 negative x squared, take away 3. Tidy that up. Negative x cubed is negative x cubed plus negative x squared is going to be positive, so I can write that as 2x squared, take away 3. Let's look over here at minus f at x, where I put a negative sign in front of the entire function, which was originally x cubed plus 2x squared minus 3. And if I do distributive law for negative f at x, I will get negative x cubed, negative 2x squared plus 3. Those are not the same. This is neither even nor odd. Please try page 91, number 1, the third part, number 2, 4, 6, 7E, 8 needs a calculator, 16 and 17.